Welcome back to the deep dive. We have a very specific, very technical, and honestly a pretty high-stakes topic on the desk today.
Yeah, this is a good one.
We are looking at a stack of technical service manuals for transport refrigeration units. And usually when we look at these, it's about fixing something obviously broken. A snap belt, a leaking compressor.
Something you can see or hear.
Exactly. But today, we're looking at a signal that is a lot more ambiguous.
It's the one light on the dashboard that makes every technician, even seasoned ones, just pause for a second.
We are talking about alarm 25, the alternator check. And if you are in the cold chain, if you're the person responsible for keeping a trailer full of pharmaceuticals or, frozen seafood at just the right temperature, this alarm is tricky.
It is the check engine light of the refrigeration world. It's so misunderstood.
Right. To the uninitiated, alarm 25 looks like a simple instruction, alternator check. It sounds like the machine is saying, hey, go swap out the alternator.
And that's what happens, right? You see the code, you grab a new alternator from the parts shelf, you bolt it on, and you send the driver on their way.
But looking at the source material we have today, these logic diagrams and diagnostic workflows, that approach is, let's just call it risky.
It's worse than risky. It's practically gambling with the customer's money and your own time. If you treat Alarm 25 as a simple replace hardware command, you are missing the entire story.
It's not a dummy light.
Not at all. This alarm is a logic puzzle. It represents a specific set of mathematical thresholds, time delays, and even hardware configurations that the system is constantly monitoring.
And that is our mission for this deep dive. We're going to decode that logic. We aren't just reading the manual. We are unpacking the why behind this code. We've got the technical service documentation detailing all the triggers, the voltage thresholds, and a diagnostic path that is surprisingly complex.
And honestly, understanding Alarm 25 is what really distinguishes a parts changer from a true technician. Because as we'll see, there are some serious nuances here.
Nuances like what?
Like the difference between a check alarm and a shutdown alarm, and a massive trap involving fuses that depends entirely on which brand of alternator happens to be bolted to that engine.
I love a good trap. But before we get to the gotchas, let's establish the baseline. Let's unpack exactly what triggers this alarm. The manual doesn't just say, if alternator broken, turn on light.
No, it's a conditional logic statement, a recipe, like you said. The system is looking for a specific set of circumstances to all exist at the same time. Let's look at the most common one first. Undercharging.
Okay, so the system is running, but it's, running out of juice.
Precisely. But the computer needs to be absolutely sure. So the logic detailed in the source says, first, the engine must be running. Second, the oil pressure must be good.
Okay, wait. Why does oil pressure matter for an alternator alarm? That seems unrelated.
It's a great question. It's because the computer needs to know the engine is actually mechanically sound and spinning. If the engine stalled, the alternator wouldn't be spinning, so voltage would drop.
So there wouldn't be an alternator full to be an engine full.
Exactly. So good oil pressure confirms we have rotation. It isolates the problem.
Got it. Okay. So the engine is definitely spinning. What's the electrical trigger?
The source material specifies two electrical conditions happening at once. First, the charge amps must be less than negative 1.0 amps.
Negative amps, meaning we're actually draining the battery, not filling it?
Correct. We are in a discharge state. And at the same time, the battery voltage is less than 13.2 volts.
Okay, let's pause on that number. 13.2 volts. A standard 12-volt battery just sitting there rests at about 12.6, maybe 12.8 volts.
So 13.2? That's not dead.
Not at all. It's just not charging very hard. That's the key.
Yeah.
It's the threshold of struggling. If an alternator is healthy and running, you should be seeing 13.5, 14.0, maybe 14.2 volts.
So if the engine is roaring away and you're sitting at 13.1 volts, you're technically failing to maintain that optimal charge.
You're not dead yet, but you're losing the war. That's a good way to put it. So less than negative 1 amp flow and less than 13.2 volts. That sounds like a pretty clear sign of a bad alternator to me. Why isn't that enough to just trigger the alarm instantly?
Because of the environment these units live in. This brings us to the third, and you could argue the most critical variable, time.
Okay.
The source explicitly states that these conditions, the low amps, the low volts, they have to persist for 3 straight minutes.
The 3-minute rule. That feels like an eternity when you're talking about electronics. Why wait so long?
To prevent false flags. Think about what happens on a trailer. The compressor clutch engages. That's a huge magnetic load.
Right.
A condenser fan kicks on. Maybe the truck hits a massive pothole and a ground wire wiggles for just split seconds.
So you'd get a momentary voltage dip.
Exactly. You might see the voltage drop to 12.9 for 10 seconds while the system stabilizes. If the alarm triggered the second the voltage touched 13.1, you'd have technicians chasing ghosts all day long.
The dashboard would just be lighting up every time the compressor cycled.
Right. The system wants to see a sustained failure. It's asking itself, is this just a blip or is this the new reality?
And if it stays bad for 3 minutes, boom, alarm 25.
Boom.
Now, you mentioned undercharging, but the sources also flag the opposite problem, which I find really fascinating. The system is just as scared of too much power as it is of too little.
Absolutely. This is the overcharging scenario. And honestly, from a hardware damage perspective, this is the really scary one.
So what's the threshold there?
The logic is similar. Engine running, oil pressure, good. But the battery voltage exceeds 16.0 volts. And again, for 3 minutes.
16 volts. That's cooking the battery.
That is frying the battery. You are literally boiling the electrolyte. You're creating a hydrogen gas buildup. But even more importantly for the technician, you're risking the control boards.
The brains of the operation.
Yeah. These units run on microprocessors. They're robust, but they aren't invincible. If you shove 17 or 18 volts into a 12-volt board, you let the magic smoke out.
And the consequence here, the source material makes a very specific distinction between these two scenarios, right? The undercharge one we talked about. That sets as a check alarm.
Right. An amber light. The unit keeps running. It alerts you, hey, I'm not charging well, fix me soon. But it keeps the cargo cold.
But the 16-volt scenario,
That's different. If it hits 16.0 volts for 3 minutes, it sets as a shutdown alarm. Red light, the unit kills the engine immediately.
it has to.
It has to. It's a self-preservation move to protect all the electronics from high voltage damage.
So undercharging is a check, oh, look at me when you get a chance. Overcharging is a shutdown, stop everything before we explode.
Generally, yes. But there is a twist in the source material regarding the, let's call it the personality of this alarm. It can change its behavior based on what the unit is trying to do.
This is the sleep mode nuance, isn't it? I found this part really interesting because it feels like the machine has a different set of priorities when it's just napping.
It absolutely does. Remember how we said the undercharge condition, the less than 13.2 volts, is usually a check alarm?
Yeah.
Well, if the unit is in sleep mode, that exact same condition becomes a shutdown alarm.
Wait, really? So if the unit is sleeping, trying to save fuel and just monitor the cargo, it becomes more aggressive about the alternator voltage. That feels a little counterintuitive.
It makes sense if you think about the goal of sleep mode, though. The unit is only waking up to do two things. Check the temperature and charge the battery.
Okay.
If it wakes up specifically to charge the battery, runs for 3 minutes, and fails to raise the voltage, there is no point in continuing to run.
It's just burning fuel for no reason.
Exactly. It's a death spiral. If it keeps running with a bad alternator, it will eventually drain the battery until the engine can't even crank. So the logic decides to cut its losses. It shuts down to save what little life is left in the battery and flags the operator.
That is a subtle but critical distinction. If a driver calls you at 3:00 a.m. saying the unit shut down with alarm 25, knowing whether it was sleeping or running continuously really helps you diagnose.
Context is everything. And we shouldn't gloss over the electric mode either. A lot of these units run on standby electric power at the dock.
Right. Checking the notes here. It says the logic still applies, but the engine oil pressure check is obviously gone since the engine isn't running.
Correct. Instead, it looks for frequency. The source notes say it looks for an alternator frequency greater than 100 hertz.
Which basically just tells the computer, hey, the electric motor is spinning the belts, so the alternator should be spinning.
That's all it is. And if it sees that frequency, but the amps are still below negative 1.0 and volts are below 13.2 for 3 minutes.
Alarm 25. Same logic, different power source.
Precisely.
So we have our triggers. We know the math. 13.2 volts on the low end, 16.0 on the high end, negative 1 amp, and that 3-minute timer. Now, put yourself in the shoes of the technician. The truck rolls into the yard. The light is blinking. Alarm 25. What do?
Well, I can tell you what you don't do. You don't open the toolbox. Not yet.
Step 1, put the wrench down.
Step 1 is always data. I cannot stress this enough. The diagnostic procedure in the source material starts with this exact instruction. Download the Service Watch data logger using WinTrack.
This is the CSI phase of the repair. You're reconstructing the crime scene.
It is. And you need to review the data using the technician user level. That gives you the high-resolution data. You want to see exactly what the volts and amps were doing at the moment the alarm was set.
Because, like you said, the alarm triggers after 3 minutes of failure. If you just walk up to the unit and stare at it, the problem might not be happening right this second.
Exactly. The data tells you where to look. If the data shows a massive spike to 16.5 volts, you aren't looking for a loose belt, you're looking for a voltage regulator problem. If the data shows 12.0 volts and it's dropping steadily over an hour, then maybe you're looking at a belt or a bad connection. The data just clears the fog.
Okay, let's say we've looked at the data, we have our clues, now can I pick up the wrench?
Now you can move to the physical unit, but even then, keep it simple. The very first physical check listed in the diagnostics is the alternator drive belt.
The low-tech solution. I like it.
It's the mechanical transfer of power. Is the belt there? Is it loose? Is it glazed over?
Define glazed. For someone who might not be a mechanic?
Sure. Glazing happens when a belt slips. The friction creates a ton of heat, and the rubber surface becomes hard and shiny, almost like glass.
So it looks okay, but it's not gripping.
Exactly. A glazed belt might look fine from a distance. It's not snapped, but under load, it just slides over the pulley. You would be amazed how many sophisticated electrical diagnostics are performed on units where the belt is just slipping and flopping around.
Verify the physical connection first.
Okay.
So belt is good, tension is good. What's next?
Live verification. We need to see what's happening in real time. The procedure says to start the engine or electric motor and go to the gauge display in the maintenance menu on the unit's controller.
So we're back to looking at the screen.
We're comparing what we see in reality to the triggers we already discussed. We are looking for that Goldilocks zone. Voltage must be greater than 13.2 volts, but less than 16 volts. And the current flow, the amps, should be greater than negative 1.0 amps.
So if you're staring at that gauge display and you see 12.8 volts while the engine's roaring,
Yeah.
you've confirmed the problem is active right now.
Correct. And that leads us into the electrical deep dive. This is where we start chasing the electrons through the system. We need to verify the connection.
The source lists checking the alternator connections, which is obvious. But then it gets into excitation voltage and sense voltage. Let's unpack those terms because they are crucial for this specific alarm.
Sure. An alternator isn't like a permanent magnet generator that just makes power because it spins. It needs a wake-up call.
Okay.
It needs an initial injection of voltage to create the magnetic field that allows it to generate power. That's the excitation voltage.
So no excitation, no power output, even if it's spinning at 5,000 RPM.
Exactly. It's just a spinning paperweight at that point. The diagnostic step is to check the excitation voltage right at the alternator terminal. The rule is simple. It should be equal to battery voltage.
So if you have 12 volts at the battery, but 0 volts at that excitation terminal, the alternator will never turn on.
Never. And the source mentions something specific here about units with the 0T3 interface boards. On those units, that wake-up signal, the alternator excite voltage, is controlled by a specific output on the board.
So if you're missing that voltage at the alternator, you need to backtrack to the board itself.
And the board gives you a clue. The manual mentions checking the interface board test mode. There is a visual cue you can look for, LED 18.
LED 18, okay. I like visual cues, they're simple.
If LED 18 lights up on that board, it means the computer's trying to send the signal. It confirms the logic is working. So if the LED is on, but you still have no voltage at the alternator, you've just got a broken wire or a bad connection somewhere in between.
That is a huge time saver. Looks for the little light. If it's on, the board is doing its job. What about sense voltage?
Sense voltage is the alternator's way of reading the room. It monitors the battery voltage so the regulator knows how much to charge. If that sense wire is broken or corroded, the alternator is basically flying blind.
It doesn't know what the system needs.
Right. It's like trying to heat a house when the thermostat is broken. You either freeze or you overheat. The rule there is the same. Sense voltage should be equal to battery voltage.
Okay, so we've checked the data, we've checked the belt, we've watched the gauge display, and we've verified excitation and sense voltages. But we haven't talked about the fuses yet. And looking at this source material, this seems to be the place where the most mistakes happen.
This is the fuse trap. It's the one detail that makes you look like a genius if you know it and drives you absolutely crazy if you don't.
So there's an easy one first, fuse F20.
Right. Step 7 in the diagnostic procedure, check fuse F20. It's a 2 amp fuse on the interface board. That's standard. Check it, make sure it's not blown. Simple.
But then We get to step 8. And this is where the brand of the alternator becomes the single most important piece of information you have.
This is the critical distinction. Step 8 focuses on fuse F4. It is also a 2-amp fuse slot on the board. But whether a fuse should be there or not depends entirely on the hardware.
Let's break it down. Scenario A, you pop the hood and you see a press-to-light alternator.
If it's a press-to-light alternator, fuse F4 must be in place, it has to be installed, and it cannot be open or blown. The press-to-light system relies on that circuit to function correctly.
Okay, press-to-light equals fuse F4 installed. Now, scenario B, you look in there and you see a Bosch alternator or maybe a Thermo King branded alternator.
If you see a Bosch or a Thermo King, fuse F4 must not be installed.
It has to be an empty slot.
Completely empty. If you put a fuse in slot F4 on a system with a Bosch or a Thermo King alternator, you are creating a misconfiguration that will cause problems.
That is wild.
Yeah.
Because usually when you see an empty fuse slot, your first instinct as a technician, someone who wants to be helpful and thorough, is to think, hey, something's missing here. I should put a fuse in.
Exactly. It's a natural instinct to fill the gap. You think, oh, the last guy forgot this. But in this case, filling that gap on a Bosch system is actually sabotage.
You're creating a problem.
You are bridging a circuit that shouldn't be bridged. And conversely, if you're working on a press-to-light system and you think, oh, F4 is optional, and you pull it, you've just broken the charging logic.
This is why the source material highlights this so clearly. It's a binary choice, but you have to know what you're looking at. You can't just blindly follow a check all fuses routine.
You have to identify the component first.
It brings us back to what you said at the very beginning.
Yeah.
Distinguishing a parts changer from a technician.
A parts changer checks if the fuse is blown. A technician checks if the fuse is supposed to be there in the first place.
That's a great line. Is it supposed to be there? So we walk through the logic. We understand the trigger's voltage, amperage, the 3-minute delay. We've gone through the service watch data, the bell check, the board outputs, and now the very specific fuse configuration.
Oh, we have.
Let's talk about the resolution. The manual has a specific note on how alarm is cleared, and it's very short.
This alarm is cleared manually. That's it.
Meaning it won't go away just because you fix the problem.
Correct. Some alarms are self-clearing. You know, if the engine cools down, the high coolant temp light might go off on its own. Alarm 25 is not one of them.
Why not?
The system forces the technician to interact with it. You have to acknowledge the failure. You have to physically go to the keypad and say, I have addressed this, and manually clear the code.
It's forcing accountability.
It is. It prevents the scenario where an intermittent loose belt triggers an alarm, then tightens up for a second, clears the code, and leaves the driver just wondering what happened. If alarm 25 sets, it stays set until a human being says it's fixed.
So if you're listening to this and you're staring at that blinking light, you now have a roadmap. And it doesn't start with throwing an alternator at it.
Please don't. Start with the data. Look for that 3-minute pattern. Check the belt tension. Verify your excitation voltage is matching the battery. Look for LED 18 on the board. And for the love of everything mechanical, look at the brand of the alternator before you even think about touching fuse F4.
And Press-to-Light needs it. Bosch and Thermo King don't. Write that on your hand if you have to.
It'll save you a lot of headache.
Before we wrap up, I want to leave you with one final thought to mull over, something that really struck me in the logic. We talked about how the system shifts from a check alarm to a shutdown alarm when it's in sleep mode.
Right, the aggressive shutdown to save the battery.
It makes you wonder about the priorities of the machine's logic. In normal operation, it prioritizes keeping the cargo cool above all else. It will run with a dying battery. It will run with warning lights screaming just to keep that compressor turning.
The cargo comes first.
True. But in sleep mode, it prioritizes the machine's own survival. It sacrifices potential cooling to save the battery voltage. It's this fascinating hierarchy of needs programmed right into a refrigeration unit. When is the mission more important than the hardware? And when is the hardware more important than the mission?
That is a deep philosophical question for a box full of cold air. But you're right. It's a programmed survival instinct.
It's all in the comment. Thanks for diving deep with us on Alarm 25.
My pleasure.
Check your fuses, watch your voltage, and we'll see you on the next one.
Stay safe out there.